I study ancient writing as the material component of literacy and numeracy. For writing, I analyze change in the material component for what it reveals about change in behaviors in brains. And for numbers, I am interested in how written notations relate to precursor forms like fingers, tallies, and tokens. You might wonder how cognition is studied in extinct populations. Material forms like written characters imply behaviors like handwriting and psychological functions like vision and language. When interpreted through the neuroscience of literacy, change in the material form implies change in behaviors in brains. Conversely, behaviors in brains help us understand the material change. I use a theoretical framework, material engagement theory, that sees cognition as a system composed of brains, bodies, and material forms. The idea is that interacting with a material form like writing changes behaviors in brains, like the changes that occur today when we learn to read and write. Changes in behaviors in brains then change the material form, as we will see in the discussion of ancient writing. Finally, material change reflects and thus accumulates change in behaviors in brains, and this distributes the changes to new users when they learn the material form. Let's start with literacy, the ability to read and write non-numerical language. The literacy we enjoy today is the result of the material form that is writing changing in its form and functions, and the brain reorganizing neurologically to interact with it. The material and neurological components have developed complementarity, meaning that both have changed in ways that maximize the efficiency of their interaction. Early writing changed substantially in its form and functions. Early signs conveyed ideas through resemblance and convention, but were ambiguous in terms of language. Later signs could specify the meanings and sounds of specific words, but no longer resembled the objects they once depicted. To understand what these changes imply about behaviors in brains, we first need to know what makes a brain literate. In a literate brain, the region that recognizes physical objects has been trained to recognize written objects, interpret them through the gestures of handwriting, and associate them with the meanings and sounds of language. Brains recognize objects topologically, that is, through their visible structural features, the spatial relations between those features, and contextual clues. Brains then predict and fill in anything that's missing. For example, here you might see a cube. The features and relations are circles with cutouts, and your brain fills in the rest. The features and relations are still there when the object is deformed, but recognition now involves tolerating its physical ambiguity. Character recognition is similar. You likely see the words the cat, though both middle characters are ambiguous. Recognition and meaning involve topological recognition of the characters, tolerating the ambiguity of their forms, the context provided by adjacent characters, and learned associations with language. Brains learn to recognize written objects when people interact with the material form that is writing, that is, when people learn to read and write. Today, handwriting is known to improve fine motor skills, hand-eye coordination, lexical retrieval, recognition and recall functions, and tolerance for ambiguity in how characters are formed. Handwriting was critical in the emergence of literacy because it made the material form malleable, relative to things that are stamped or impressed. And malleability enabled the material form to change, so that it reflected, accumulated, and distributed changes in the behaviors and brains of the writers. Early signs were meaningful through resemblance and convention. But once signs were recognized topologically, they no longer needed to resemble their original forms. Once the need to resemble was relaxed, and because they were malleable and used together as sets, signs were freed to become defined against one another. Over time, the set converged on features that strongly activated the visual system and helped identify characters and tell them apart. Features also became more subtle, an effect of familiarity. Signs also simplified as proficiency in using contextual clues reduced the need for detail, speeding up both production and recognition. Signs for numbers and then words emerged in the mid to late 4th millennium, signs for sounds in the mid-3rd. Obligatory word order and determinatives provided greater specificity in representing language, and as specificity increased, writing became identifiable as Sumerian. Wedge order standardization shows productive behavior becoming automatic, freeing attention for the content of writing rather than its mechanistic production. By 2000 BCE, literacy is signaled by several phenomena. Words were no longer split between lines of text, an integrity of form that implies topological recognition. Cursive shows a tolerance for ambiguity that implies handwriting effects. Writing was applied to many new purposes, showing it had achieved significant expressive power. Training was highly formalized because script could no longer be understood without it. And finally, overall change also decreased around this time. So far, writing has represented ideas, so let's look at how it became able to express language and then a visible form of it. As shown, an animal, a figurine, and a sign have recognizable commonalities of form. Simply, we identify them as oxen because they look like oxen. But none of these forms expresses language. Certainly, written signs, like the material objects they resemble, can be named or described in language. However, being named or described is very different from the sounds and letters whose combinations represent the word in English. Combinations of sounds and letters are forms of language. In this regard, the written sign on the top has more in common with the object it resembles than it does the letters on the bottom. Writing began as pictures and diagrams meaningful through resemblance or convention. Resemblance and convention were adapted to represent sounds through the rebus principle and acrophony. In comparison, an alphabet is a set of symbols that mean individual sounds whose combinations form words like the sounds of speech do. Letter combinations are recognized topologically and associated lexically through the processes we've already discussed. Alphabets first appeared as Egyptian hieroglyphs used for their initial consonants, a form of acrophony. Signs for vowels were added later by the Greeks. Before the first alphabet emerged, writing for words and syllables, training effects on behaviors and brains, and formalized instruction had been available for over 2,000 years. Simply, alphabets were possible because the necessary conditions were already in place. Mesopotamian literacy isn't necessarily a universal model. In Egypt, writing underwent two substantial changes in morphology, while in China it underwent one. These changes were differently timed and sequenced relative to Mesopotamia. These differences are likely related to the different social purposes for writing and the effects these had on writing behavior. It's also possible we might not see the earliest writing in these places, particularly China, whose Neolithic notations significantly predate the Shang script. Nonetheless, the brain regions and functions involved in literacy are consistent across languages, cultures, and writing systems. Thus, while there are differences in timing and sequencing, the systems of writing that developed into literate traditions have more in common than they differ. I'm going to shift focus now to numeracy, the ability to reason with numbers. Neuroscience, linguistics, and ethnography provide cross-cultural insight into the psychological, linguistic, and behavioral dimensions of numbers. Archaeological and textual data provide insight into the material component of ancient numbers, spanning their early realization through finger counting to their elaboration as a complex mathematics through the use of written notations. Numeracy involves the parts of the brain that appreciate quantity, know the fingers, plan motor movements, and make decisions. It's essentially a cognitive system for manipulating material objects like fingers, tallies, and tokens. The language functions aren't highlighted here because numeracy doesn't significantly involve them. A part of the visual word form area becomes specialized for numbers. This number form area connects to the regions of the brain involved in numbers, rather than those involved in language. Numbers begin with the perceptual experience of quantity. It works as follows. Here are 10 groups of tally marks that range from 1 to 10. The range of 1 to about 3 or 4 is subitizable, or rapidly and unambiguously appreciable without counting. As we will shortly see, numbers begin as subitizable quantities. Without counting, groups of more than about 4 are appreciable only as many, and as being larger or smaller than each other if the difference lies above a threshold of noticeability. Because their quantities are subitizable, written characters for 1, 2, and 3 have conserved across thousands of years. Beyond the subitizing range, marks tend to be rearranged as subitizable subgroups. As rearranging is a finite strategy, a higher group is replaced with a convention that means a bundled quantity. In decimal systems, this occurs at 10. When numbers first emerge, they count no higher than about 3 or 4, consistent with the perceptual experience of quantity. They also lack the productive grouping that forms higher numbers from smaller ones. An example of emerging numbers comes from the Munduruku people of Amazonian Brazil. In comparison, the earliest written numbers reached amounts in the hundreds, tens of thousands, or millions. These ancient numbers were also productively grouped. So when numbers first appear in written form in the ancient world, they have already been elaborated well beyond the level associated with emerging number systems, and this means these number systems were already old by the time writing was invented. Symbolic numerals and associated concepts emerge from the perceptual experience of quantity through a systematized sequence of material forms, starting with the hand. Over time, the concepts of numbers become increasingly different from the original percepts. Numbers acquire properties from the material forms used to represent them. The explicit material form becomes increasingly concise, and in response, users must supply a larger amount of knowledge. Numbers also become distributed over multiple forms, so they become independent of any particular form. We will look at two of these transitions more closely. The first shows that numerals share form and functions with their predecessors. The second shows that numeral forms change due to handwriting effects. Tokens, impressions made with tokens, and notations that look like tokens are identical in terms of their form and functions. They share shape and size, and they mean by repetition and bundling. Repetition repeats elements, while bundling consolidates repetition. These material forms also differed. Tokens were loose, while notations were fixed. This made tokens manipulable and suitable for calculating, while notations had an integrity of form that made them suitable for recording. Numerals are influenced by both the perceptual system for quantity and the other processes of change that govern handwriting. Because their quantities are subitizable, numerals with 1, 2, and 3 elements tend to conserve, though they can become cursive, forms with greater ambiguity. In Mesopotamia and Egypt, groups with 4 or more elements were rearranged into subitizable subgroups. In the Egyptian lineage, these forms became the cursive known as hieratic. With demotic, the non-subitizable notations continued to change through handwriting effects like topological recognition. They would become symbols. While numbers don't need to be written, writing significantly changes them. Written numbers become objects recognized through their features rather than collections of objects like tokens. Written numbers are highly concise, a property enabling the collection of relational data at unprecedented volumes. As scribes learned and applied these relations, calculation became a matter of manipulating relations rather than physical counters. Writing was also used to record calculation methods as narrative descriptions of the steps involved. In these ways, writing facilitated the elaboration of numbers into a complex mathematics. Numerals are semasiographic, representing their meaning without phonetic clues. They are semasiographic because they share form and functions with precursors like fingers, tallies, and tokens. Once techniques for representing sound values were available, they were not applied to the Sumerian words for numbers for centuries, and then only to small numbers. Sumerian words for large numbers were not recorded for more than 1,000 years after writing was invented. This lag occurred because numerals work better as numbers without the visual clutter that phonetic clues add. That is, there must be a reason to add sound values to numerals since they work better without them. In this case, scribes who spoke Eblaite apparently wanted to learn the Sumerian words for numbers in addition to the Sumerian numerals. For us, it would be like learning the Latin names of the Roman numerals. This research lets us understand how societies of average people achieve complex systems like mathematics and literacy. The insights generated are not just applicable to how complex cultural systems developed in ancient times, but to the coevolution of cognition and culture in general, including our own, present, and future. Thanks very much for your attention.